The topic is, the area is heterogeneous brittle solids. This is a follow-up, really it's a follow-up talk to a few remarks that I have made a couple of years ago. The last time we met in Cisterna with a small subgroup of this audience. Essentially, heterogeneous solids and structure are materials that have a random microstructure, and essentially this is an actively researched topic because, of course, these are brittle materials, especially are materials that fracture following an initiation process. So even if there is no previous damage, so we have an initiation process, then there is an evolution with the formation of several microcracks that nucleates and then cooperate together to actually determine a localization and a global catastrophic failure with no evident warning usually. So we have a microscopic effect, failure, driven essentially by microscale phenomena. So bottom-up, or essentially discrete microscale approaches are natural approaches. This remark is perfectly in line with Professor Kyriakides. This morning he said, I'm a discrete guy. I'm not going that far as to say that I am a discrete mechanics person, but this is probably the part of mechanics I have been explored most. Now, let's take the simple 1D damage model due to Kachanov. Really, he introduced that in the context of creep, but then this model had a tremendous success, and of course, it's a scalar model with all the limitations and all the benefits that comes with it. Now, this is seemingly simple. However, how we determine the damage parameter that really describes the complexity of any damage process is really absolutely non-trivial. I'm going to go real fast in the first part so that I can actually set the stage and then spend a few minutes on the continuum part so that I tune myself more with the audience. Now, when we deal with the discrete microstructure-based approach, we have to recognize that there are several length scales that we can think about the problem. We have a macroscopic length scale, then we have usually, if we are able to model with a continuum at the scale, we are able also to define a representative volume element where we can actually, over width, we can actually average random properties, random fields, and random parameters. Then if we increase, if we zoom in, if we use a microscope to look into the material at a finer scale, we actually are able to discriminate the microstructure, for instance, the polycrystalline structure of a polycrystalline material. And then you will see microcracks nucleating, micro, submicron crack nucleation between grains. Then if you increase again your resolution, you go down to the atomic scale. Okay, doesn't matter. Let's say that we play between these two length scales. So we need a macroscopic length scale, which is a structural, the sample dimension. Then we have a microscopic length scale, which is, for instance, in this cartoon, is the grain size. Okay, our objective is to establish the connection between discrete models of damage and suitable representative continuum models based on first and second gradient theories. Now, point of departure. Discrete models capture the microstructural geometry and mechanical properties, offering a bottom-up tool to study the effect. So let's try to see what is the physics like at the finer scale, and then let's try to build a continuum model that are physically based, that respects the physics. Background. Okay, I don't need to go back and forth. Okay, the simplest model, the simplest damage model is the fiber bundle model. Probably most of you have seen this. It's a little bit more than an exercise, but it's an excellent starting point because for this type of system where you have lots of N bars, which are elastic, and they have some microstructural, microconstitutive law, and they are all connected together with a rigid bar, essentially you can come up with closed-form analytical solutions. This is relevant so that you can get a clear picture of some of the things that happen at the macro scale and then reflects on the macro scale. Now, for instance, if we try to apply the Kashanov model, it takes this form, and essentially you immediately are able to derive the damage parameter, the mean damage parameters, as an integral of the distribution of the critical strain of these links. These links are simply elastic elements that at a certain point, at a certain threshold that is random, breaks down. So what happens? You have a global sharing rule, so the load that is not essentially taken by the broken link get redistributed evenly over the survival links. Now, together with this, and of course you just sample critical distribution for any sampling distribution, and you come up with all sorts of damage parameters simply by integration. You can also calculate the variability of the response, because this is a random model. If I have a population of critical strain, I just sample n of them, and then based on my sample I will have a certain evolution. So mean, response, average, but also scatter. This is nearly always neglected, especially amongst the continuum community, I must say. So average is fine, we will be talking about average behavior, but don't forget that there is also a scatter. Now, there are lots of systems where you really cannot stop with the 1D representation. Most material systems resemble higher dimensional system, like this lattice, which simulates a polycrystalline material. And then there is an obvious complication that is evident from the definition of the damage parameter. This is what I just shown you. This is what we will be discussing later on. You can see at a glance that is much more complicated. So these are some examples of materials that can be described or simplified in terms of network descriptions. You can see definitely this network formed by the grain boundaries. These are just pictorial things that I'm throwing at you. You can see nanoscale cracks on brittle phases in multi-phase materials, and you can see cracks propagating through a polycrystalline material that has been embrittled by exposition and by creep deformation for 10 years at 900 degrees Celsius. So, let's say that from those material systems we can come up with a simplified representation that is a lattice based on typical Delanoy simplification. So each grain gets associated, maps into a node in the lattice, and all grain boundaries map into links. Now, when you simulate a tensile or compressive test on this system, you actually get this type of response, sigma epsilon in stress strain response. But now something very interesting happens. If we try to understand why this comes about and how this relates to the microstructural properties, you have to look into microstructural quantities. And if you do simulations, and we actually wrote the code so we were able to control anything about this model, so it was a nice virtual lab, we were able to actually go and investigate properties as we pleased. You will see that as I apply a strain in a displacement-controlled simulation, of course, I will induce the rupture of springs that can sustain strain of the same order only until a certain point. Then something happens. There is an explosion. When I get when I approach the peak of the stress response, you see an explosion, and what happens essentially, there is a damage localization, energy localization, and also springs that are very strong gets broken, of course. There is an avalanche, and so the system experiences a transition from a homogeneous deformation to a localized deformation. So I'm just saying things that several of the previous speakers already brought in the picture. Now, let me point out something very interesting. In that specific lattice, you had some horizontal links that were aligned to the direction of the load, and then you had some diagonal ones. Then, if we if we check essentially the behavior independently of the horizontal link and the diagonal spring, what happens is this. The links that are favorably oriented with the load tends to break at a faster pace, at a higher damage rate in the beginning. You see the red spots. And this is perfectly normal, but it's also something that gives you a tremendous perspective about this phenomena. Now, the diagonal one essentially don't participate in the damage process until a certain point where when the damage rate increases and then explodes. Beyond this point, as I was saying, no matter if you are a diagonal or if you are a parallel link, you will be part of an avalanche. There is no way the microstructure can stand the energy redistribution. Now, this is another interesting point. If we consider what is the nature of the building block of this process, is really the fact that when I remove a link because there is a microcrack that nucleates into the microstructure, since the very first one, like in this case, you immediately have a perturbation, elastic perturbation field that irradiates over the domain. Now, this is the effect of a microcrack forming on horizontal links. Now the test direction is this one, okay? Now if I go and check the same effect on diagonal links, you will see that you have an increase of strain, elastic strain induced on the other surviving links of 3 orders of magnitude, meaning that even if something was oriented at an angle and would not withstand any load in a pristine configuration, as soon as I start removing links, they are invested by a perturbation field that actually loads them. This is why, over time, the diagonal link gets involved into the process. And until they become so involved, they become dominant. When essentially what happens, there is damage localization, clusters of microcracks nucleates together, and you actually have now a microcrack propagating through. Now, so this is really the point I was... Actually, I mentioned already a couple of years ago, this is where we were. So this is the rational damage model for that lattice. And this is pretty much work that has been done by me and some co-workers up to 2008 or something. And this is really the counterpart of the fiber bundle model. Now, let me just point out to you that there are 3 random quantities that enter in this model. The number of broken bonds, and for each broken bond you have a parameter eta, which is a redistribution parameter, and the microstrain of the link that broke, so the critical strain of that link. Why am I saying this? Because this is a nice mathematical tool, it's the reference point for us to reason, but it's very difficult in practice to know these quantities, okay? So, why am I going to seek continuum representations? Because I want to overcome these difficulties. I want to see if I can make some educated guesses, some assumptions that let me use, instead of these parameters, which are hidden quantities to me, some more manageable quantities that I can measure from experiments, for instance, from digital image correlation. Okay, let me get to that point. So, those 3 parameters are highly random fields, okay? And only if you know them, you can actually compute these quantities and really compute exactly what the damage parameter is. And of course, if you're able to track the system, the phenomena, and you're able to measure those quantities all over throughout the damage evolution, you will be able to essentially predict real nicely the behavior of the lattice for not only tension, but also compression, and not only in X, also on Y, because of course this lattice is not really isotropic. It has an isotropy. I mean, it's isotropic only in pristine state, because the hexagonal lattice maps into an isotropic continuum. This is well known. But as soon as you introduce one defect, you induce an elastic anisotropy. So a damage-induced elastic anisotropy. And so, again, in fact, if we check the importance of the single microcrack, when I pull in one direction or when I pull in the other, the effects on the lattice are completely different. And I'll be able to discuss with you on any of these aspects later on. Let me go a little bit fast because this is just introduction. So we were fiber bundle models, and then this is the two-dimensional model, which is actually representative of higher dimensional systems. Now, let's examine continuum approximation. Okay, this is our lattice. This is our force response. And you can see there is this how they go, snapbacks, which are essentially instability effects, okay? And I think Professor Kyriakides had the entire talk based on this type of phenomena. Now, specifically, let's look at this type of data. This is the stress strain response. The simulation results is a black line. The red line is the rational model I was just mentioning. Then the damage. Hello? Doesn't work. Whatever. Okay. The damage parameter is down there. This is the failure path. And over here, I have the inputs that I need to use really the rational model. Now, have a look at the stress strain curve because it's what we really want to simulate. And then also the damage parameter, of course, which has to enter in the Kachanov's model. And this is really what I'm going to draw your attention to because I want to model that input. It's tremendously complicated, and if I manage to do that, I'll succeed. Okay, I'll go fast. First order model is very easy. If I can come up with a Helmholtz free energy, pseudo potential, I'm able actually to match nicely analytically the results. So, basically, you can do this. This is something that Professor Del Piero has done. What I've done is this. I have tried to... Works?
Yes.
Okay, thank you. I have fitted this model to the damage parameter for each type of grain boundaries or links that I have in the microstructure, and that model that I picked works nicely, and there is a meaning to it. Then, of course, something is missing there. Okay, there is the... No, it's 2 minutes. I mean, I read 18 minutes, 13 seconds, 14 now. I'm not going to take questions. So this is actually essentially the results. You can do it, no problem. So it's an exercise, you can do it, first order model, no problem. Now, second order model, just follow me here 1 minute. This is the response. I'm going to check 4 points. This is a grid where I actually measure the strain field with the digital image correlation technique. I'm going to show you what happens in the beginning when I have no damage, when I have some damage, when I am at the peak, and when I am at the failure. You can definitely see that the displacement field reveals the whole story. Then I'm checking the strain, so the first derivative, the first gradient, and then the second gradient. And the key idea in this is, can the second gradient of the displacement convey the information about the stress fluctuation, so the critical strain of the grain boundary, the inner strength of the microstructure? If I take this field, the answer is actually promising, because if I make this assumption, this is the problem here. So the critical strain in my model is approximated as with a proportional, with a constant, with the minimum of the modulus of the field, of a component of the second gradient field. You unfortunately don't see it because the resolution is pretty bad in this monitor, but this is the damage parameter, and this doesn't work again. And that's the force response. It's not bad because this is a rough approximation. Of course, there is a huge correlation. I'm gonna close pretty soon. Now I make, however, there is still some problem because I have this problem here for small damage density. So what I do, I just make a different approximation for small strain. And essentially, I come up with this model, and I stop here just to show that by using a second gradient displacement, so I'm throwing it inside my rational model, now I have a continuum quantity that I can measure experimentally, and I have enormously simplified my model, and I have an approximated model that actually matches the simulation results pretty nicely. So there is definitely now a continuum counterpart that is physically based to the rational model. Let me see if I have to say something meaningful here. Something meaningful is this, probably. This direction, this research direction, essentially is driven by the fact that we should be able to derive models that are useful for technological purposes. So digital image correlation is a non-contact full field strain measurement system. So let's use it. Now it's essentially, we have it absolutely on a routine base. The other thing is this. Through this exercise, I have realized now that the damage problem is not really a two-stage process. It's not really nucleation and propagation. But it's more like nucleation in a dilute regime, nucleation in a cross-talking regime, but still homogeneous over the entire lattice domain, and then there is the propagation. And this is of practical importance, because if you are worrying about early warnings in these catastrophic sensitive systems, this is very key, so that we know where we should go and check for critical warning signal. Sorry for having been a little bit long.
In the meantime, you can do. I have not seen how you propose damage on second grade.
Essentially, I have substituted, I have replaced one of the quantities on the random field in the discrete model with a second gradient related quantity. And essentially, this is a continuous quantity now. The model itself, it's rather trivial to actually have an entire continuum model.
So your final model, this was, I think, good in Microscale, and there was a very important assumption that you can assume that the first fiber results in the failure of the last fiber, or something in between.
But the model was abandoned and this is what the simplest version of a global sharing rule. Of course, there is all sorts, there is hundreds, thousands of papers where they actually have local sharing rules. Now, it really depends on what type of statistics you embed inside, what you were mentioning. I may not be aware exactly of their work, but I have seen it in all sorts of flavor, and the key is really what type of disorder you put inside and what type of interaction you enforce between neighboring links. But this is mostly like a textbook example for me.